think this is on. Hi, nice to meet you, everybody. My name is Fang Liu. I originally actually from China, but I went to the US in about 20, let me see, almost 30 years ago. I went to the US 1997. So, um, first I want to thank the organizer for inviting me to give a lecture here. Uh, I double checked up to, I have about 60 slides. I double checked up to like 40 slides. I was planning on checking the last 20 when I arrived in China, but my VPN was not working great. Actually, it's like door to door from my home to the hotel. It's like 40 hours during the whole trip. So it was really exhausting. So the last 20 slides, I didn't double check. Maybe you see some inconsistency or some typos. Please, sort of like maybe pardon me on that. Um, anyway, so I'll be talking about Bayesian AI safety, measurement sensitivity, decision making for large language model and agents. I'm not sure the agenda you have is up to date. Originally, I was gonna talk about synthetic data through Bayesian methods, but later on, I kind of changed to this topic. Hopefully, the agenda you have this kind of updated title. This title also, so this topic also relates to one of the project I curate. I think at least two teams actually are working on Bayesian AI safety. I know one team actually sent me an email, but as I mentioned, I just couldn't access my Gmail. I saw the email, but I will read it and respond to your question. Sorry about the delay. I know that you sent the email like 2 days ago. Sorry about that. I'm from University of Notre Dame, which is a Catholic private university in Indiana, United States, and it's very close to Chicago, maybe like a 1.5 hour drive to Chicago. I'm a professor in the Department of Applied and Computational Mathematics Statistics. I was trained as a Bayesian statistician. My research include trustworthy machine learning and AI, data privacy and differential privacy, and the Bayesian methodology and modeling. Okay. All right. So the topics that I will cover in this lecture has four modules. So the first module is data and model, right? So why a Bayesian model will be a good fit and how to specify those models given AI safety data. The second module will be on uncertain quantification and calibration. You cannot talk about Bayesian without talking about uncertain quantification. And the third module will be adaptive red teaming and the decision making. And the last module will be a case study. It's kind of like integrate all the knowledge from the first three modules and give you kind of concrete example how to use the Bayesian model to model AI safety data. But kind of a primer, right? So why we are talking about Bayesian approach for AI safety evaluation? That's because Bayesian methods and modeling is a natural fit because what we observe from AI safety evaluation, the data is a noisy surrogate for some underlying unknown latent variables. We're actually genuinely interested in measuring, but because it's latent, it's unobservable, and what we have is noisy surrogates. And Bayesian is known for kind of latent variable modeling, so it's a natural fit. And also Bayesian decision making is based on robust quantification with uncertain quantification. And if we want to make a robust decision, and Bayesian comes into this picture kind of in a natural way as well. So this will kind of give you give you an overview, overarching kind of a frame, why Bayesian will be kind of one of the approaches that you could use for AI safety assessment. So this is kind of the structure of this lecture. So the first module will be about 30 minutes, and second module will be about 25 minutes, and we take a 5-minute break. So I usually don't go on like for 90 minutes. That's just too long, right? So everybody need a break. You need a break. I can need a break. Everybody can kind of refocus after break. Feel free to go out and grab water or go to restroom. So module 3 will be about 50 minutes, and the last module will be a case study, about 10 minutes, and we take 5 minutes kind of to summarize the lecture. So after first 3 modules, I will have kind of 2 questions, right? So if you have a phone, right, so smartphone, and if you can, I have a QR code, and you can scan the QR code, and there are multiple choices questions, A, B, C, D. You can choose A or B or C, and you think that's the right question. So I'm gonna do a sort of online poll, and to see how well you have sort of absorbed in the material that cover each of the modules. So just two questions. It's anonymous, right? So I'm not gonna record your answer. Right. Okay, so move on to, by the way, any questions so far about the structure and the setup of this lecture? All right, oh, good. Okay, so module one, Bayesian framing of AI safety evaluation and data in the model. So this is the learning objectives for this module. So after this module, you should be able to distinguish a latent safety relevant event and population estimate. Estimate basically is a very fancy statistical way of sort of saying this is a parameter we are interested in estimating, right? So this is sort of differentiate those target parameter from the parameter we're not interested, but you have to have that in the model that's like a nuisance parameter, but estimate are the parameters we're interested in estimating from the noisy labels observed in AI evaluation task. And you should be able to formulate a hierarchical Bayesian model for variations across models and the context, environments, and judges. There's like different sources of variation that sort of goes into this noisy surrogate. Hopefully through Bayesian model, you can sort of decompose this total variation into different components. And the lastly, after this module, you should be able to interpret posterior quantity and posterior predictive quantity for deployment relevant safety risk. All right, so first some notations and nomenclature. So we denote an AI model by small letter m, and rater and judge by R. This could be human rater or large language model rater or judge, and the evaluation time by small t. And we denote the context or evaluation case by C sub I. So this kind of a bundle of everything, right? So could include the user query, intent, the context history, and system prompts, and agent environment, and task type, right? So whatever you can think of that kind of goes into this context or evaluation case. So the evaluation, the context follows the evaluation distribution, right? So we denote this distribution by P eval, and that's the data we have. But we are genuinely interested in how safe this AI model is after deployment, right? So there's a deployment distribution for this context, and we denote this deployment distribution by P deep, right? Depth. And that would be the distribution of situations that the model will face after deployment. And sometimes we're interested in knowing kind of where the model performed really, really bad. We kind of try to understand this kind of rare events, series, failure. We denote this, usually we can do that through adversary testing and red teaming, right? So we denote those cases by the distribution that those cases come from by P adv, right? So adversarial distribution. When you kind of query, interact with the model, you set up the context, and the model give you an output, right? So we denote this output by O, big O, and that's also a probabilistic distribution given a model and evaluation time. The true safety event is a function of the context and the model output. And we denote that by Z. Okay, so, and this is something that's not observable. This is something we're interested, but unfortunately, this is latent. This is not observable. Z does not have to be binary, but for illustration purpose, I just gonna focus on Z being a binary safety event, right? So one will be unsafe behavior, could be harmful compliance or hallucination, and etc. And zero will be like not unsafe behavior, right? But it can take kind of maybe a category or sort of a leveled category or something like that. But as I mentioned, for simplicity, we're just focused on binary event in this course. Z is not observed, but what we observe is Y, which is the noisy surrogate of Z or noisy proxy of Z. And for example, if you interact with the AI model and the model give you an output, right? So and whether this output is safe or not, truly it's Z. But we cannot observe that. So we have a human judge or a large language model to kind of label whether the output is safe or not, and this is why, right? So that's why compared to Z, it has one additional kind of subscript, which is R, denotes the judge that used to kind of label this output, whether that's safe or not, right? So hopefully you understand the difference between Z and Y, and Z is what we are interested in estimating, and it's a probability, right? So the probability that Z equals Y, Z is equals 1.
Okay, just wait for 1 minute.
What is that?
It is the start of a regular lecture.
Oh.
Like in the university.
Okay, it sounds like a lullaby. You put students into sleep. Very calming and soothing. That's it. All right. Yeah, so Z is something we're interested but not observable, and we are interested in the probability that Z equals 1, which is the probability that unsafe behavior occurs. But we don't observe that. What we observe is Y. Could be multiple Y's for one Z, right? Depending on how many judges you have, how many raters you have for judging the safety of output. All right. So just kind of give you some concrete idea of what this kind of latent variable is, right? So Z could be truthfulness of an answer, right? So, but we use kind of measurement, right? So instrument to measure whether it's really truthful or not, right? So it could be just label that correct or incorrect answer, and but the challenge with this measurement is that it could be partially true, right? So it could never be probably cannot be captured by a binary kind of correct or incorrect answer indicator. And harmful of compliance, right? So it could be refusal or compliance label, which is binary. But again, and the measurement challenge is that there's always rubric uncertainty and stuff like that. And for agent safety, and there could be trajectory success or failure, which is a binary. But safety, if you interact with the safety, it's like it's a sort of a trajectory, and there could be long horizon and two effects and how environment changes. And again, like kind of a binary observable proxy probably is not the ideal, but this is what we have. Okay, so given why, how we can infer using Bayesian approach on the probability of Z equals 1. In all the examples, and we also kind of experience like a judge-rater bias and proxy validity and ambiguity and the concept dependence and rare events and data sparsity, that kind of real world scenario. Okay, so all those are reflected in Y. That's why Y is different from Z. So I'm not going to go through this table one by one, but hopefully the slides can be shared with you after the lecture. So you can refer to this table later on, but there's some like large language model safety benchmark data that you could use. For example, Anthropic red team 2022. So they actually, the labels they have is a graded 0.4 attack success rating. It's not really binary. It's really a kind of well-known data, and the other one is the truthful QA, which is a well-known data as well. It has both sort of binary true or false reference set as well as the multiple choices scoring, and so on and so forth, right? So this is LLM safety benchmark data set, and of course there's some other sort of AI agent-related safety benchmark data sets like agent harm and agent dojo and agent safe bench. Yeah, so again, due to time constraint, I'm just gonna skip the detail, but feel free to refer to the table after the lecture once these slides are being shared with you. Questions so far? Gonna get a little bit technical after this slide. All right. So as I mentioned, estimand is just kind of fancy name of saying the quantity that we're interested in estimating, which is an unknown parameter. So the estimand that we're interested in estimating is the probability that model M produces a safety relative event when it is used in the deployment environment. So as I mentioned, the Z is a latent variable, and is the probability of Z equals 1 integrated over the distribution of the outcome given the model and given a context. Okay, so Q of M given C, basically is the probability we observe a safety event given context C in model M. Of course, C follows the distribution, right? So, and if we further integrate this uncertainty around C over its distribution, we get pi of M over the distribution of kind of deployment setting, right? So you further, so take expectation of Q of M given C, right? So over the distribution of context, and this is the final parameter we're interested in estimating. And the larger M, basically we're focusing on Z equals 1, right? So larger M basically means there's more risk associated with this model or it's less safe, right? So it's a probability of unsafe behavior. And human reader and large language model judge as noisy instrument of Z, right? So, and we do not observe Z, and what we have is Y, and not, the judge are not perfect, right? So if we have perfect judge, we don't need Bayesian model for kind of infer the latent safety event, right? So every judge is also different, right? So we have sensitivity of judge of judge R. That's a probability. Basically, it's the true positive rate or recall rate. So if there's indeed a kind of unsafe behavior, and judge R will be able to identify that, and that's denoted by mu1 sub R. And specificity of judge R is the true negative rate, right? So if there's no kind of safety, unsafe behavior, how likely judge R will be able to tell that, right? So that's denoted by mu sub 2, okay? Because we don't observe Z, we don't know mu1 and mu2 either, right? So mu1, mu2, they are also unknown parameters. All right, so that's LLM and the sort of setting. And if we deal with the AI agent, it becomes more kind of complicated because we have a trajectory rather than kind of a pair of like context and output. And what we have is there's a state at a time t, and there's outcome at time t, and based on the outcome, you take a certain action, right? So AI agent takes a certain action. So we have kind of a trajectory until it finishes, the whole episode finish, and you have kind of whole trajectory. There's multiple ways of defining a latent trajectory level safety event, right? So the example I have here is we observe at least one safety relative violation during the whole trajectory, right? So, but you could use other sort of safety you could define other safety measurements, right? So could be at least like 2 or something like that, right? So or the total number of unsafe events, or maybe there's a disastrous event, right? So severe sort of safety violation, right? So there are like multiple ways. Yeah, so as I mentioned, the safety, AI safety is often trajectory level property, and there are multiple ways of defining that, but from a statistical perspective, it's sort of the same thing, right? So let's say we are focusing on observe at least one safety violation, right? So, and Z of tau, which is the trajectory, is the probability that Z equals 1, and you kind of take over all the context, take over the distribution of all the context, you get the probability of Z equals 1. Yeah. Okay, so what we have kind of talk about so far implicitly assume that the evaluation distribution is the same as the deployment distribution, right? So all roughly the same. If we sort of evaluate the safetiness of an AI agent or large language model, it can be automatically sort of extrapolate to the deployment setting. But that's not always the case. Sometimes there's a distributional shift, right? So what you evaluate, what the real world deployment scenario might be different from the evaluation data, okay? So when the deployment distribution is absolutely continuous with regard to the evaluation distribution, mathematically you can write that way, or if something not gonna happen in the evaluation data set, that's never gonna happen in the deployment setting either, right? So that's another way of saying kind of absolute continuous with respect to the evaluation distribution. And we can define the importance ratio. Okay, so NP is the sort of you can think of that as a CDF, a cumulative density function, a cumulative density function, and the D of P give you the PDF, probability density function, right? Okay, all right. Yeah. So if this absolute continuous continuity assumption is true, you can define the importance ratio, right? So because like when eval is equal to zero, this is not defined, but as long as eval is not equal to zero, and this importance ratio can be defined, kind of give you a likelihood ratio or density ratio of of a context, right? So yeah, so if what we have, what we're interested in is the theta parameter that with regard to the distribution of, with regard to the deployment distribution, but the data we have is the p-val, right? So it's the evaluation set. But we can kind of use the change of variable trick, right? So you multiply and divide the the way the integral, the inside of the integral, and they cancel out. But you can sort of derive that importance ratio, and but now you're switching from integration over the deployment distribution over the integration over the evaluation distribution, right? So if you look at after the conversion, right? So if you look at the expected value of Q, right? So different from what we had before, if you recall. Where is it? Yeah, so this is what we're interested in, right? So, oh, yeah, so sorry, there's a pi, that should be theta. Okay, so if you compare this, right? So this is the expected value of Q of C over the distribution of deployment. If there's a distributional shift, you just have to weight this Q of M by the importance ratio, right? So that's where the importance ratio comes in, right? So everything else remains the same. It's in the ideal situation when the evaluation and the deployment distribution are exactly the same, W equals 1 across the board. Now, if they are different, sort of you sort of give different importance kind of measurement to different Q of M. Sort of, yeah, reweight this Q of M so you can evaluate the probability of unsafe event under the deployment setting. Okay. If the importance ratio is unknown, you can always use sensitivity analysis, right? So, and in the Bayesian framework, you can put a prior, right? So on this important ratio, right? So to kind of incorporate uncertainty about this important ratio into the final inference on theta. If an adversarial user select their own prompts, adaptive selecting, right? So, and the deployment setting will not be IID, right? So that's, and it could be, it cannot be, in many cases, it's not benign anymore, right? Yeah, so as I mentioned, this framework depends on that the WC, the importance ratio is defined. If p-val, in some cases, we just don't have any data at a certain context that will be of interest in the deployment setting, What we can do is either you can make some like a strong model assumption, right? So you can extrapolate what we have into a scenario we never seen before, or just go ahead and collect more data, right? So to make sure that this important ratio can be defined. All right. Questions so far? All right. So I have 5 examples, okay, to show how you can use the Bayesian model to model safety data. AI safety data. The first one is really kind of a very basic, Bayesian model. And for simplicity, we focus on a single time point, t, right? So I draw a subscript t in this example. And what we observe is a label y given context c sub I from model M by judge R, okay? And we can specify the likelihood function, and z is binary, and obviously we can use Bernoulli distribution with a probability pi, and given, sorry, I'm switching back and forth between pi and something like that. I think it's theta, right? So sorry, this is pi is the probability of z equals 1, and we could sort of model the logic of pi sub im as a function, as a linear sort of function of I plus theta m plus beta. Alpha is, I have a follow-ups. The interpretation of each of the terms is on the next slide. But alpha is sort of like the baseline model risk, right? So, and the theta m represents the deviation of risk deviation from the baseline model or the average model, population average model. For model sub m, beta I represents the deviation in context from the sort of baseline model given context I. And what we observe is y, right? So, and from z to y, right? So this is the sensitivity when times z, and plus 1 minus specificity 1 minus z, right? So that gives you the probability of y equals 1, right? So it comes from 2 sources, right? So from the true positive source and from the false negative source, right? So this capture both the sources of y because the judge is not perfect. And that's a likelihood function, right? So the whole thing, only y is observed and everything else is latent. And as a Bayesian, you have to put priors on those parameters, right? So for alpha, if you don't know anything about alpha, just specify its prior variance as a really large number, 1,000, 1 million, whatever, right? And for theta m, beta I, this is where you could kind of do a hierarchical prior, allow you to pull strength or borrow information across different models and pull strength or borrow information across different contexts, which is really, really helpful if you have like really sparse data from a certain model or really sparse data from a certain context setting, right? And theta m and beta I, a priori, they can follow a normal distribution, but we could put another prior on sigma theta rather than set it as a constant, like a known constant, right? So if one of the commonly used prior on theta, sigma theta and sigma beta is half normal distribution, you could use others, right? You could use inverse gamma distribution, but half normal distribution is proved by research that give you kind of better results, like less biased, right? So especially in data sparsity setting, okay? And mu1, mu2, because they are parameters between 0 and 1, natural prior will be beta distribution, right? So if you don't have a lot of information, a priori information about the sensitivity and specificity, just set A1, B1 as small value, right? So 0.1, 0.1, right? So, or 1, 1, right? So if you set A1 equals 1, B1 equals 1, it's U will be follow a uniform distribution between 0 and 1, right? But you could use other settings as well. Yeah, so those kind of give you the full specification with the likelihood function. Prior, you can derive the posterior distribution and obtain posterior inference on Z and any of those parameters that in the likelihood function. So as I mentioned, so those are some of the interpretation of those parameters in the model. Alpha is the overall baseline log odds of safety events, and that's usually a nuisance parameter. This is something we're not interested in estimating, but we have to have there in the model, right? The latent terms, theta m is what we're interested, right? So this is the latent unsafe event propensity score for model M, or deviation from average model. And beta sub I capture the deviation due to a certain context compared to an average sort of baseline context. Gamma sub R is the rater or judge effect or deviation from kind of an average rater or judge effect. As I mentioned, the Bayesian prior, why Bayesian is great, especially when data is unbalanced across different models or different contexts, right? So it just allows you kind of assume everything from a super common population, and it kind of allow the kind of information pooling, which is the major strength of Bayesian modeling in this setting. And you can also kind of obtain the inference on posterior predicted distribution of z given y, right? So you can measure that and to see how like those judges agree with each other, right? Depending on the variance of z given y, maybe that can give you some idea. Maybe you can assess the quality of the judges. Okay. All right, so that's the first example. Second example is context-dependent judge sensitivity and specificity. So what we have in the first basic model is that every judge actually have the same sensitivity and specificity across all models, across all contexts, but that's a really, really strong assumption, right? So model, their sensitivity specificity could vary across different context models and observable responsive characteristics and rather than fixed. So if you want to model that, bring that flexibility into the model, you could sort of leave mu1, mu2. You can model mu1, mu2 as kind of at another kind of model layer, right? Because mu1, mu2, there are probability as well, and it makes sense to do the logic transformation on mu1, mu2, and we can model them as kind of you can even bring some of the covariance of the judges or task types or context depending on environment, whatever, into this model, right? So to see how sensitivity and specificity vary by judges and vary by different context settings or different models, right? So, and again, all those parameters are unknown parameters, and you have to kind of add priors onto those parameters and derive the posterior distribution. All right. Okay, so example number 3 is a rare failure model, right? So not every failure is common, right? So some of the failures probably is common, hallucination, like AI models, ChatGPT hallucinate all the time. It's getting better over time, but some of the failure is more catastrophic, right? So you don't see that quite often, maybe just every 1 million time you see a rare event, right? So if you don't observe a failure event, that doesn't mean it's a zero risk. You just don't have enough data yet. Maybe the benchmark or the evaluation data set you have is a really narrow scenario. It doesn't cover the setting where this failure can occur, right? So zero, you observe zero failure doesn't mean it's zero risk. So give you a concrete example, okay? So for illustration purposes, let's just forget that we have an oracle judge, means that the judge basically knows everything, right? So with a 100% sensitivity and specificity, and we just kind of we kind of lose one layer of modeling from Z to Y to make the modeling framework a little bit simpler, right? So we can directly model the likelihood of a failure using Y, and let's say we just focus on one model, one context, right? So and different models, and this theta m follows a beta distribution, and beta distribution is a conjugate prior for Bernoulli likelihood function. What that means is that the posterior distribution is also beta distribution with a closed form posterior distribution formulation given by this. This is really, really well-known results. And yeah, so this is, you can treat A as a sort of a priori safety occurrence, and minus B is a priori sort of safe occurrence, like, yeah. And S is the failure, you observe the failure, number of failures, and N minus is the total number N samples or cases. N minus S is the sort of not unsafe behavior. I will not say safe behavior, right? So it's not unsafe behavior. Let's say S equals 1, right? So S equals 1, this is the posterior distribution of theta m given y. S equals 0, I'm sorry. And you plug that in, you get the posterior distribution. And if theta follows this sort of distribution, right? So you can get the probability of theta is greater than kind of a tolerance level, whatever you feel that's appropriate for a given setting, right? So you could say my tolerance level for a really bad event is like 1%, right? If you plug in 1% in, and for, let's say for prior, I specify A equals 1, B equals 1, right? So that basically says a priori theta follows a uniform distribution, can take any value from 0 to 1 with equal probability, right? So if you plug all those in, let's say we have 100 cases, even you observe 0 failures, there's still 36% probability the failure rate is greater than 1%. That's really, really high, right? So if you, this probability is very sensitive to N because data sparsity, because it's a rare events. Let's say you only have 10 cases, the probability that the safety, the unsafe behavior will occur with a probability greater than 1% is equal to almost 90%, right? So even you observe any unsafe event. Without Bayesian, you cannot obtain that, right? So this is purely because Bayesian framework and the prior specification. Of course, like when data is sparse and how prior specify will have a big say on what this probability is, right? So if you specify A equals 0.1, B equals 0.1, those two probably gonna decrease, right? So but regardless, you can use Bayesian to obtain kind of this rare failure probability, even there's no unsafe event observed. Okay. All right, so example 4 is a localized conditional risk. So what we have focused so far is kind of an average risk over the deployment setting, but it could be the model is safe in most of the deployment sort of a sample space, but there's a small region, there's a big spike, right? So it's just kind of become unsafe in that particular region, right? So you wanna, you will be able to kind of identify that region. So what you can do is that use a semi-parametric Bayesian model, kind of bringing the Gaussian process into modeling how the risk changes with different contexts, right? So rather than kind of a fixed parameter, beta I in there, which is kind of says, okay, context I give you the same deviation from the baseline safety baseline. Now it can vary. The deviation depends on where this context comes from, right? This phi is a numerical embedding, mapping the context usually is context into kind of numerical values, and you use Gaussian process, which is non-parametric, right? So you are not assuming any functional form, just leave the data to figure out. Yeah, to model this kind of, hopefully you will be able to identify that region and to see where there's a big spike in safety behavior, right? So yeah, and again, and the rest is basically the same, right? So I assume that you have some basic working knowledge with regard to Gaussian process. This is kind of a kernel function that models the correlation or covariance of the function at two neighboring data set x and x prime. Okay. Yeah, this is slightly more complicated, right? So why is it called a semi-parametric? Because alpha and theta, they are parametric. They are responsible for the parametric part, and the Gaussian process model is known as a non-parametric modeling component, right? So combine the parametric and non-parametric part, you get this semi-parametric model. Yeah, so once you kind of specify the likelihood functions, the prior, you can derive the posterior risk, local risk, right? So for each of the C contacts, you can derive its corresponding safe behavior, probability of having an unsafe behavior, right? So and with corresponding uncertain quantification. This is just one example to model this, right? So if you suspect that there's some localized conditional risk, there's a region that with high risk cannot be picked up by a constant kind of parameter in the model. Some other model you could use is kind of use a Gaussian mixture model or something like that. Use rule-based subgroup of discovery or recursive partitioning, but they are not, the last two are not quantitative, right? So they are more like exploratory and descriptive methods. Okay, example number 5 is the agent evaluation model. As I mentioned, agent evaluation is more complicated because you are dealing with a trajectory rather than just a pair of like context and outcome, right? Basically they are the same. The model look exactly almost the same, except for you have additional latent variables in the likelihood function, right? So you have u in this particular example, I have u of z, which is kind of give you environment difficulty to kind of for the environmental deviation from the base model, and this is kind of interaction between environment and some of the episodes or things like that, right? So this is not like kind of standard, do whatever you want, right? So just put additional latent variable into the model, right?
What is gamma in the field?
What's that?
What is gamma? Gamma vector.
Oh, gamma is regression coefficients. Z covariates are observed. The gamma are just kind of regression coefficient. You can use basic, so just like beta, whatever slopes, all right, so okay, so that's 5 kind of examples of Bayesian model. After you obtain the posterior distribution, this is quite standard, right? So rather than use kind of binary, making a binary claim, model A passes the benchmark or not, you can formulate a probabilistic statement, right? So we saw that before, right? So the probability that unsafe event the unsafe event occurs will exceed 5% is what, right? So it's 50%, right? So or it's just 1%, right? So depending on the threshold you use, and you can decide whether you want to release the model or not, right? So it's more robust rather than just use a binary kind of cutoff. And that's estimation understanding of unsafe events. And the other one is prediction or forecasting. So it means that you have to formulate the predictive posterior distribution, right? So given a new context CY, I want to formulate what's the posterior predictive distribution given this new context C of Y, right? So this is the likelihood function, right? So if you look at the inside the integral, this is the likelihood function that we specify, and this is the posterior distribution we obtain given the likelihood function, given the data, given the prior. And so basically you draw samples from this posterior distribution of psi and then plug that in, and you can sample Y from the likelihood function distribution, and you have a bunch of like samples from the posterior predictive distribution, and given this posterior predictive distribution, you can kind of quantify, right? So do probability that the number of, I don't know, like the probability that Y M equals 10, right? So out of maybe 1,000 sample is what, right? So you can formulate kind of whatever statement that you want to make or probability y equals 1 is greater than something. This is much better than just kind of descriptive statistic without Bayesian, right? So if you want to do forecasting, if you don't use Bayesian, you probably just summarize, okay, and in the past like 100 cases, I observed like 10 failures, and there's a 10% probability this will occur again, right? So, and the new setting might not be observed, right? So in any of those evaluation data sets, right? So even extrapolation. All right, so the other thing that you could do with Bayesian is a posterior predictive check, a PPC. It's a really kind of a model evaluation technique, right? So it's how good my model is for the data, for the given data. So what you can do is that, okay, you draw repetition of the evaluation data set. If I kind of collect data from the same underlying population distribution of Y, you can repeat this like 1,000 times or like 10,000 times, whatever, right? You're gonna end up have like 1,000 or 10,000 sets of data, and you have a set of statistics you want to evaluate. For example, could be the failure rates by given a certain prompts, right? Or a rare events summary, right? So you're gonna calculate that statistic in each of the representative data set. And you calculate that statistic in this in the original observed data set, and basically, like, let's say this is kind of a distribution of t, y rep, right? Let's say t is the number of like rare events, right? Whatever events could be, I don't know, like the AI did something really, really bad. And this is where the observed statistic, right? If this observed event is a typical value from this distribution, this basically says that the model is a good fit for this model, right? So if this kind of statistics really kind of locates in the tail of the distribution, means maybe the model is not a good model, at least from this statistical perspective. You can formulate whatever statistic and evaluate the goodness of fit with regard to this statistic, right? Yeah. So this is different from establishing deployment validity. This is more like a check of whether the model I have is a good model for the data I have, right? Yeah, so that's posterior predictive check, and the other thing is called a prior predictive check. It's interesting, right? So rather than drawing parameters from the posterior distribution, you are drawing parameters from the prior distribution. So why this is helpful? Because Bayesian inference can be sensitive to the prior. You want to evaluate how Bayesian inference is kind of different if you have different prior, and help you to understand, interpret prior through the behavior that they imply before observing the evaluation data. Right? The procedure stepwise, procedurally speaking, is the same as a posterior distribution, just drawing the parameter from the prior distribution rather than from the posterior distribution. And given each of the drawn parameters, you're gonna sort of specify the replicate of y, and you do the same thing, right? Yeah, so and then given the formulated statistics, you can ask a bunch of like questions regarding the prior, right? So how that sort of look different from the observed value given the data, right? Kind of understanding what this prior says before you observe the data regarding the failure rate. All right, so that's kind of ends module 1. So just to summarize, AI safety evaluation is a measurement pipeline. As contexts are sampled, and model generate outputs from a distribution, and judge, they produce noisy labels. And we define our main target of interest, which is the kind of the probability of unsafe event occurs in the deployment setting. And we specify several kind of Bayesian, hierarchical Bayesian models for kind of capture the uncertainty or the variation from different models, the context or judges. And we talk about what if the posterior distributions, what if the deployment distribution is different from the evaluation distribution, how we can use importance ratio to make a correction. Okay? And we also talk about like the posterior predicted distribution, prior predicted distribution, and how to use that to evaluate model fit to understand the specification of prior. All right, so with that, as I mentioned, I have a couple of questions. If you have phone, you can scan this QR code and read the question. You can select A, B, or C. I think I should be able to, let me, sorry. Oh. I hope I have a dual screen so I can see the response. How can I, without,
Maybe some kind of split screen.
yeah.
Or maybe, by the way, this thing is a presentation, and the presentation can be shared with all participants. So you can open the presentation and transfer code to your laptop. And for responses, you can open it.
Oh, okay. All right, yeah.
Okay, also you can share to monitor more than specific
This is actually, I could see the real-time sort of response. Like I use a poll everywhere, but I cannot go to the website. But anyway, so maybe just take a minute and think about this question and what's the right answer. Anyone? Do you want to shout out the right answer? Yeah. Oh my God. Okay, never mind. Yeah, So maybe I didn't, yeah, I should have activated the questions. What's that right answer? What's that? B? A? B, yeah, B, yeah, it's B. All right. All right, the second question. Given the basic Bayesian safety model fitted to several prompt family, what is the appropriate Bayesian prediction for a failure probability of model on the unseen prompt family P star? So if you recall the model we have, oh, this is fancy. Okay. Something is logit. There's like beta m. There's beta I, right? So I is the context, okay, and this is the baseline. This is the model deviation from the baseline or average. And this is model the prompts, right? So all context I deviation. Okay. What will be the right answer? What's that? C. Yeah, it's C. Okay. All right. Somebody said D. I mean, like, even you read this, like, if you see something, you use the only, right? So that means it's not right. Well, anyway, so let me see. So, no, I mean, you want to integrate out like any uncertainty and to focus on the parameter beta. You cannot like just arbitrarily setting some of the parameter equal to 0. Just doesn't make sense, right? It's just not equal to 0. Anyway, so all right. Okay. How much time do I have left? Wow.
30 minutes.
What's that?
30 minutes.
30 minutes. Okay. All right. All right. So the second module, probably gonna go this the rest of the presentation really quickly. The second module is on uncertainty and calibration. Okay. So after this module, you should be able to differentiate different type of uncertainty in the setting of an AI safety evaluation. Understanding what is the calibration, which is different from uncertainty, right? So and understanding that Bayesian predictive probability distribution probability is not automatically calibrated, right? So you have to calibrate before using those Bayesian predictive probability to evaluate AI safety. And there's like a black box sampling procedure that you can draw kind of output from, and for Bayesian AI evaluation as well. So this is slides summarize different type of uncertainty, right? So there's two ways of categorizing uncertainty. One is by whether additional evidence can reduce this uncertainty, right? So there's aleatoric uncertainty that means that it's the randomness or uncertainty is inherent, right? So it's just there in the world. And the other one is epistemic uncertainty, which can be reduced by acquiring more knowledge and getting more data. And if we kind of that's one sort of dimension that we can categorize different type of uncertainty. The other dimension is that when the uncertainty enters in this context, the AI safety evaluation, right? So that could be semantic uncertainty, right? So if we deal with LLM, right? So there could be judge reader uncertainty, and there's real context, real world context uncertainty. There's a two environment uncertainty if we are talking about AI agent, and there's a normative, right? So even everything else is kind of like a minimal uncertainty is minimal, but the normative can vary in different settings as well. Aleatoric uncertainty is, as I mentioned, it's the inherent uncertainty or noise in the data that cannot be eliminated. For example, if a sidewalk delivery robot asks that, is it safe for me to cross now? Like even the robot has the perfect sensors, but there's always residual uncertainty that maybe something like because like suddenly appear in the robot's path that the robot does not sort of never, this is just happened in the real world, right? So regardless how perfect this robot is, like there's always uncertainty around this kind of things that suddenly occur that the robot cannot be 100% certain, okay? And if in the event of a aleatoric uncertainty, which is really large, that make you uncomfortable of releasing or deploying AI system, you should abstain, right? So just kind of I'm not ready, right? So because the aleatoric uncertainty is so large, that's the kind of safety action you can take in face of aleatoric uncertainty. Epistemic uncertainty is reducible, right? So, and using the same sort of example, the deliverable robots as is specific for me to course now, there's uncertainty may be caused by a block camera view, right? So maybe there's like the data that used to train this robots is not perfect, right? So there's a missing sensor or traffic sensor or something, but this can definitely be remedied or kind of the uncertainty around these things can be reduced by kind of maybe making a better version and gather more information and collect new data. Right. So in the face of epistemic uncertainty, what are the AI safety actions, right? So as I mentioned, you can gather more evidence, maybe defer, right? So retrieve information or escalate to human review or something like that. So from a Bayesian perspective, how we can sort of decompose understanding those two sources of uncertainty. Let's say we're interested in predicting a future safety outcome Y, giving a new context, right? So we have this posterior predictive distribution, right? So we saw that before, right? And the posterior predictive variance of this Y new, actually this is kind of just a simple total variance decomposition, but you can sort of regard the first term as the aleatoric variability and the second one as the epistemic uncertainty, right? So the first term basically reflects the variability remains under a fixed data generation model, right? Which is inherent, right? So, and the second one is that that there's always an unknown model parameters or latent variables that kind of goes into epistemic uncertainty, okay? Semantic uncertainty arises because large language model outputs are often long form, and is meaning based, right? So different words may express the same answer, right? So if you look at those two, and they're token wise look very different, right? So but they basically have the same meaning. Um, and sometimes for the same query or for the same prompts, it might the same model might give you two conflicting safety claims, right? So let's say like the prompt says, can I give this leftover medication to my friend? And if you ask the model today, the model might say yes, because as long as they have similar symptoms. You ask the model tomorrow, because it's stochastic, the model might say no, medication should not be shared because of, yeah, so it really depends on individual. Right, so those are two conflicting safety claims that might come from the same model actually, even, yeah, so this is like a semantic uncertainty. Uh, if you use token level entropy, they might not be the best sort of metric for capturing the semantic uncertainty. What you can do is use the semantic entropy to measure semantic uncertainty, right? So some of the tools listed there, you could do semantic clustering, right? So kind of have like semantic equivalent class, and once you have those classes, you can use just kind of derive the semantic entropy. That's a better reflection of how vary those outcomes are in terms of meaning, rather than just kind of surface level kind of token. And you can also use judge-based review to kind of assess whether, of course, this can be expensive, right? So if you use human judges, but anyway. So this is another way of kind of quantify the semantic uncertainty. This is basically what I just said on the previous slide. Given a context C, you could sample from the same model. This could be a black box AI model. You don't have to know the weights or whatever, just kind of a query. Oops, sorry about that. You just keep querying the same model many times, give the same prompts, like this is the self-consistency assessment, right? So, and you give all the outcome, you're gonna kind of have cluster those outcomes into different equivalent class, and calculate the semantic entropy, right? From a Bayesian perspective, if you want to put any like interval estimation, uncertainty quantification on P, any of those probabilities that it belongs to a certain semantic like equivalent class, or even put any uncertain quantification on entropy itself, right? So you could use a multinomial distribution to model the frequency of the classes, each of the classes, and use the Dirichlet prior on those probability, right? So, and again, this Dirichlet is a conjugate prior of multinomial likelihood function, and the posterior distribution of P given all the data is also Dirichlet distribution, and you can directly kind of obtain the posterior inference on all those P's and on semantic uncertainty, okay, the uncertainty around this on semantic entropy. Deployment uncertainty, that's kind of very straightforward because we actually don't know what the real world looks like. No matter how good the evaluation data is, there's always something that's unexpected. Yeah, so, and in presence of deployment uncertainty, what are the safety AI actions, right? So you could do stress testing, right? So monitoring, right? So keep monitoring, right? So, and kind of take actions and report sensitivity of the model to different distributional shift. For AI agents, there's additional kind of uncertainty sources, right? So there's the two environment sources, which to use, what kind of environment the AI agent deployed to. There's a trajectory uncertainty, right? So it's a long horizon path, right? So anything can happen, right? And the AI agents, there's also policy updates, model updates, right? So this kind of affects how AI respond and AI behavior and subsequently their safety behavior as well. now revisiting, like we talk about different type of uncertainty, let's revisit how those uncertainty enters the beta model, Bayesian safety model, right? So the context come from its own deployment sort of context distribution, right? So the output come from the model being stochastic, right? And the like the even the true underlying label on on uncertainty on unsafe behavior that's subject to normative sort of different norms and things like that, right? And why, of course, that's a noisy observation, right? So if you kind of write this all out, kind of Bayesian really help you to think through all those uncertainties and how to model this uncertainty. What model I use? What are the unknown parameters? What are the assumptions, right? So even eventually you choose not to use Bayesian, but just writing everything out really help you to think through. Maybe helps you with other modeling tasks, right? So yeah. All right, so I think I talked about this already. Like you could use treat AI model, even you don't know what's going on inside. You can use that as stochastic simulator, just kind of keep drawing the output to give the same prompts and to assess how consistent the outputs are, even with the same, even given the same prompts, right? All right. Okay, calibration. Uh, Bayesian inference determines how uncertainty is combined and goes into inference. Calibration is different. Calibration is measures the reliability or trustworthiness of a probabilistic predictor, right? So it checks whether stated probability corresponding to the observed probability. It's external property, right? So to the fitting model, right? So everything can be calibrated, to be honest. And also this is calibration is often assessed on held out data set from the same population where the probability claim is intended. Okay. It's not Bayesian. Something I want to mention that even I kind of talk about calibration in the context of Bayesian lecture, but this calibration is not uniquely Bayesian. So if I sort of, if we put calibration in the context of AI safety evaluation, let's say we have a Bayesian model, right? We fit a Bayesian model, we have data Y, and we get we use the Bayesian model, we can estimate the probability that Z equals 1, we denote it by P hat. What calibration asks is that among all the events where I say there like probability unsafe event occurs is P, it really means that if I kind of go ahead and collect data, really there's the probability that this unsafe event occurs really has a probability of P, right? It's now you are not overstating that probability, not understating probability. You are just kind of stating the probability as is, right? Yeah, so and the Bayesian probability may be miscalibrated under model misspecification or distribution, right? So you have this kind of data model, and we formulate Bayesian models and given likelihood function prior before you take any action based on the Bayesian probability. There should always be a calibration step to make sure the probability says I'm 80% confidence that the unsafe event occurs, it really occurs 80% of the time, right? So it's not like occurring like 90% or occurring 10%, right? So you need this calibration step to make sure the model is reliable. Okay? And there are certain kind of diagnostic technique or tools that you could use to evaluate whether a model is calibrated or not. One is called a Breyer score, and the other one is called expected calibration error. Yeah, so the Breyer score is strictly proper scoring rule, which I have on the next slide, how this is defined. But expected calibration error is sort of like you have to kind of cut the observed probability into different beans And within each beans, you see, okay, this bean says like 90%, you just kind of, 90% of like probability you're gonna count within that bean is really like something happens with 90% probability, right? So you're gonna evaluate that, and kind of you have this bean error, and just kind of get the weighted sum. Prior score is more complicated. It's actually decomposed into different components. There's a calibration error. This is really by definition, right? And there's also resolution component, which is like measures how well the prediction distinguish groups, which generate different outcome probability, right? Even a model is like perfectly calibrated. It might not be like have a great resolution, right? So just saying everything is like a 50% probability, there's no resolution whatsoever, even though it could be like perfectly calibrated. And this is a sort of inherent uncertainty with regard to the outcome, right? So Breyer score has all those kind of components that goes into its final formulation. So as I mentioned, Breyer score is a strictly proper scoring rule. It incentivizes a forecaster. Have about 15 minutes. Yeah. What's that? Oh, okay. All right. So yeah. So it's incentivize a forecaster report its true probability rather than systematically exaggerating or understating its confidence, right? So what that means is that if the model kind of a forecaster believe that the probability that y equals 1 is equal to q, like the expected loss will be minimized. You have a unique minimizer at q, right? So yeah, so this is what Breyer score can do, but like the expected calibration error, it does not have this kind of property. It's more like a diagnostic tool, but Breyer score, you can directly treat that as a loss function and to achieve a calibration and also get the model parameter estimate at the same time, right? All right, so sorry about rushing through, but this is the module 2 summary. And we talk about different sort of uncertainty, and depending on which kind of criteria you use, there are different ways of categorizing different type of uncertainty. And we talk about very briefly talk about calibration. It's not uniquely Bayesian, but you need to calibrate a Bayesian sort of predictive error or Bayesian posterior probability before you use that for doing AI safety assessment. All right, so I have a couple of questions as well. Maybe take about like 30 minutes on each of the question. Maybe just say what the answer is after reading the question. Sorry, I think we have to forego our 5-minute break. I'm really way behind schedule. What will be the right answer? Yeah, it is B. All right. Okay. Second question. Yes. Okay. All right. I have a couple really smart students in that area. The rest of the students is so silent. I know you are very smart. You're just kind of very shy, right? That students, you are very well calibrated, right? So you are confident about your answer. You are 100%, right? So you are kind of not very well calibrated, not very like maybe a little bit kind of should be confident. Yeah. Okay. All right. So some module, red teaming and Bayesian decision making. All right, I'm gonna be rushing through this module as well. So let me just skip this slide. Yeah. So we talk about Bayesian model, Bayesian uncertainty. We talk about like a calibration. But that's not decision yet, right? So it's just kind of numbers, right? So, and how to transform those numbers into decision rules and decision action. There's something else that you have to bring into kind of the whole picture, right? So what we have talked about so far is the first component, right? So statistical uncertainty, right? So that comes from the posterior distribution and posterior predictive distribution. But when you talk about decision rules and certain and actions, there's like what are the available actions, right? So there's the action space, right? So deploy and deploy with restriction, defer, right teaming, or whatever, right? So and there's the consequences, right? So it's not like you make a decision, I'm gonna kind of deploy the system, right? So there's a consequence if the system is not 100% safe, right? Or you choose to defer, it might not be the best decision either, right? So there's a cost associated with deferring, right? So that's the cost that Anthropic has to pay because OpenAI released their model first, even though like Anthropic said they had their model first, but they want to be 100% sure the model is safe before releasing, but they paid a price, right? So people talk about ChatGPT all the time, right? But anyway, so yeah, so there's just like from those numbers to actions and to decision making, there's something else that you have to bring to the picture. Um, uh, and those things, don't ask me, I'm a statistician, right? So those things they are more operational and policy driven and ethical choices, right? So we are responsible for that part. But you are more than welcome to contribute to the other two components. But we can help to formulate some of the decision rules, right? So let's say we denote the deployment volume by V and the cost per harmful outcome by CH, H stands for harm, and delay deploying a system by C of D, and the labeling, if you decide to collect more data, and you have to label those new data, and that's labeling cost CL. Some of the decision rules you could use is that you want to choose an action that minimizes the posterior expected loss, right? So this has like you are not taking into account the actions, the sort of the additional cost associated with taking a particular action. You just want to kind of depending on how you formulate the loss, right? So if the loss already has fall into the sort of the cost, the values of taking a particular action, you want to choose action that minimizes kind of utility function or loss function. Or you could like this is a posterior expected value of theta given y, right? So theta is the probability of a failure. And rather than using kind of an arbitrary threshold, you could formulate threshold by bringing kind of maybe formulate a really meaningful kind of threshold, right? So C of D is the delay cost, right? CHV is the sort of total cost if you deploy this system. And so this is kind of a cost, delay cost on I don't know, like the company, right? So this is kind of the harm to the society, right? So if this ratio is really, really small, right? You might say, okay, I mean, it doesn't make a lot of sense to release the system now. Maybe I should delay because the cost is small, right? So if this delay cost is larger, much larger than the total cost of releasing the system, even though it's harm, you might just release it now. It's not worth it, right? Yeah, so, and the last thing as well, right? So even though we're statisticians, we deal with this part, but we can help to formulate the final decision rule by kind of marrying the kind of the numbers with the final sort of threshold or something like that. There's something called expected value of sampling information. So this is what that means is that additional evaluation itself is a decision, right? So with both value and cost, right? So it's not free, but it definitely brings additional value, right? So the more data you have, the better. So let's say if I denote A denotes a safety decision, and D denotes a proposed evaluation design, and Y new will be sort of the new evidence collected under this new design. And the current Bayesian base risk is expected sort of kind of risk of utility given the current data. And if you decide to collect new data, right? So, and under this new design, you have kind of the new base risk, minimize base risk under, if you decide to collect new data. as I mentioned, it never hurt, right? So in some sense, this is always positive, right? So with new information, new data, you always have a positive expected value of sample information. However, that doesn't mean you should go ahead and collect data because you have to bring the real life cost into consideration, right? So a C will be the cost of kind of collecting this new data or labeling whatever, right? So you want to choose a design that give you the maximum value of this, right? So as long as the value exceed the cost, and you can go ahead and collect new data. And you can also even use this to design how many, to kind of calculate how many new data points you wanna collect. Gosh, I have like 5 minutes. All right, so let me see. I think this, let me see how. All right, so maybe 1 minute on this slide. Adaptive red teaming changes estimate. So adaptive red teaming deliberately sample context using previous results. We mentioned that before. It's no longer IID. It's sort of like adaptive, right? So if I see this, I want to sort of look for the next data points that allow me to see some like failures, like catastrophic failures or something like that. And this is sort of using the same importance weighting idea to kind of help you to guide you to see where you're gonna collect the data and to kind of quantify that failure rate, okay, under red teaming policy, okay. Also, causal inference can be brought into the picture as well. I think this I think there's two teams working on Bayesian AI related project. One team actually is doing this. They emailed me. I couldn't recall which team, but they sort of like kind of running different evaluation intervention, right? So if I do this, what kind of like outcome or unsafe behavior I end up having, right? So you want to see maybe some. This is kind of this is a dual operator people use in causal inference or causal modeling, right? So if you apply this intervention, you get the expected value of z, the probability that z equals 1 occurs. If you do not like deploy this kind of intervention, could be a policy, safety policy, and this is the corresponding probability a certain event occurs, and you want to kind of estimate the difference between those under those two different interventions, and hopefully this will help to, if you deploy this intervention, hopefully it will decrease the probability of unsafe event occurrence, right? Yeah, this is kind of, you can bring some of the, this is a still ongoing research topic. If you're interested, this is definitely something that's worth kind of investigating. And Bayesian, it never stops, right? So even you get all this kind of quantities based on the evaluation data, as I mentioned, because like AI system constantly changing and environment constantly changing, and you should monitor after deployment, because you will never expect the deployment is perfect align with the evaluation data sets, right? So this is where you could use the Bayesian sort of dynamic modeling, right? So kind of bring that longitudinal factor and use the transition model to kind of keep updating the probability of unsafe event, right? Yeah, so this is this slide basically kind of give you a concrete example, right? So here you see a transit model, right? Whether there's a kind of a gradual shift in the probability something unsafe event occurs, or you allow a certain probability that a certain event just occurs suddenly, right? So this give you a transition model, and you can keep updating those parameters along the way after you collecting new data after the model is deployed, okay? Yeah, so because I rushed through module 3, I don't expect you know the answer. Maybe you know the answer. But anyway, there's two kind of questions on module 3 as well. Please do take a look after the lecture. So just maybe a couple minutes on module 4, the case study, which is kind of interesting, which is kind of a Bayesian jailbreak detection with LLM judges. So this kind of set up a red team suite of adversary prompts is run against model M. Each response either complies with a harmful request, which is a jailbreak, or it refuses, right? So and a human, you don't have the kind of the all the resources to label everything, right? So but you use kind of LLM to judge the score every response, safe or not, or jailbreak or not. But you do have the money to hire several human kind of labelers, and that give you the gold labels. We call that the calibration set. And the question you will ask is that, is the jailbreak rate low enough to ship, right? So whether I'm ready to deploy this system. And the latent variable is Z. It's truly a jailbreak. And we're interested in estimating theta, the probability that jailbreak, which is the jailbreak rate, what we observe is Y. And human labels on a certain subset of those responses. And we saw that before, right? So this is kind of combining the sensitivity and specificity to give you the expected value of Y, which is a noisy label. And if you don't use Bayesian, you could overestimate the jailbreak rate, almost like 6-fold higher than the true jailbreak rate, right? So which is really, yeah, I don't have time to, but anyway, so you just plug in the numbers and you get this, right? So if you just use directly the expected value of Y bar, which is the sample sort of the expected value of Y, the estimated jailbreak rate is like 6%, but the true jailbreak actually is 1%, right? So, and the precision is like 50%, means like 80% of those kind of flagging that this is a jailbreak is actually false alarms, which is really, really bad. Why this happens? Because this is a rare event, okay? And use Bayesian, it will help kind of dealing with that kind of situation. You don't run into this kind of the same problem. And we specify the likelihood function and all the priors. The posterior, it looks a little bit sort of nasty, but to be honest, like all those priors, they are conjugate priors of this likelihood function. Turn out they are not that bad at all. Even you use a Gibbs sampler, every step of a Gibbs sampling actually is really, really quick. You don't have to use MCMC at all. Like you can draw from the closed form sampling posterior distribution. But anyway, so after sort of running all those kind of Gibbs sampler, and you can obtain the posterior mean of theta, and you can quantify the probability that theta is greater than 2%, greater than 1%, or something like that, right? So I make a decision. It's much better than rely on kind of the average noisy label rate, right? So which can overestimate or underestimate the true jailbreak rate. Okay. All right. So I don't have time to. You know what? Let me just stop here. I don't want to. Yeah. So the sum of the slides. Yeah. This is like. Yeah, the question is BC, right? So the answers, this is for me, at the beginning I said I have like a B, so I can remember all the answers, but yeah, those are the right answers to the questions, and those are some of the references, and yeah, I think that's it. I have some like kind of, yeah, if you're interested in learning the sort of the Gibbs sampler in the jailbreak example, here are some of the concrete steps. But anyway, so I'm gonna stop right here. Thank you so much for your time. Yeah. Okay. What's that? Oh, okay.
Here we go.
Okay, the question is that you mentioned, like many times in your talk, that you have kind of internal technical problem of estimating the density ratio between like some density P and Q.
Yeah.
And kind of an adversarial and deployment setting, and how one should actually approach the solution of this. How to estimate this ratio of densities.
Oh, are you familiar with Metropolis Hastings algorithm?
Yes, yes,
This
yes.
is the same thing, right? So you can assume so the best scenario. Let's say this is P deploy, and the best scenario is that P evaluation is like this. P eval.
Yeah.
Yeah, but the situation, do we have a different color? Yeah. So maybe the deployment is not like this. Maybe it's have the same support. It's still kind of on the same domain, but it might look like this. This is still workable, right? So because I have the same domain, I know the distribution I know the distribution of those two. I can directly calculate ratio, right? So uh, the two sort of really bad scenario is that the deployment sort of is something like this. You actually don't observe this part.
Yeah.
As I mentioned, you one way is that you make assumptions. You just kind of assume like this is gonna extrapolate like this, right? So from the evaluation distribution, or you collect more data, so hopefully you can fill in this space. Uh, and yeah, so would be a really bad scenario to deal with, but still you need to have some understanding of what this deployment distribution is, right? So have some data, even though it's not perfect aligned. As long as you know what it might look like, you should be able to calculate ratio. But you are still not sure, just put apart.
Yeah, yeah, it's pretty challenging, especially in high dimensions. Like typically we have high dimensionality for like LLMs.
Oh, I see what you mean. Yeah, that could be a problem for sure. Yeah.
Okay, thank you. Any other questions?
Well, then I have a question myself.
Yeah.
You're speaking about jailbreaks and somehow estimating of the risks, and that's quite a complicated business question itself. And I would like to know better how can it be described with the Bayesian analysis, because actually, first of all, there's seemingly no clear way to well, I guess to put the risks, especially taking into account that if, for example, all people know that there is at least one jailbreak, not just a distribution. People maybe would use this jailbreak everywhere, and you would not observe or guess it the simple way before all the people know about the jailbreak. So just putting the risks as numbers and optimizing them, but that's not.
How you gonna? Okay, so if let's say you have to evaluate that, right? So before deploy, like what people would do now? Like what would you do if you don't use this? Are you gonna just directly kind of observe how many jailbreaks occurs and take the average? That exactly give you this. So
Well, okay.
even this is, I will argue that even though this is a simplified model, I understand the real world is really complicated, but this is one way to at least give you a better model than take a simple average.
Well, okay.
but you are more than welcome to come up with a different like modeling framework or some other.
Well, that's quite hard. Do you know what models do people typically use in production to estimate it?
I don't know.
Well, personally, about me, if it would be possible, I would just release any model which allows jailbreaks, and that's all.
You will release any model allows?
Yeah, the freedom of speech, you know.
Oh, you are not going to release any model allows jailbreak. Is that what?
Basically it depends on the policies and how sensitive are the companies to jailbreaks. If I would be the leader of the company, I would not be sensitive and just allow any jailbreak. That's all.
Yeah, I think this is definitely, that's one of the normative like uncertainty, right? So you have to, like a different company might have different policy. Maybe some of the companies, they are more conservative, right? So they could.
Any policies just can be somehow described with the coefficients of the risks for different categories of misclassified things, right?
You mean?
Maybe the companies that would not like jailbreaks at all, they would just use the coefficients higher for this type of misclassification. I guess, right?
Sure. I guess, yeah.
That well, the question is: are those exits of decision making the only and the most reasonable option?
So here's a couple of examples. Let's say you kind of use the Bayesian model to get data, right? So you have to specify some of the sort of threshold, right? So if the jailbreak rate is like based on the posterior distribution greater than 2%, it's
Yeah.
just like it's only 1%. You probably feel very comfortable. Like if the risk is so low, I'm gonna just ship, right? Like this is like if it's greater than 2%, give you the probability that's greater than 2% is 20%. That's you can make a decision probably. I need to collect more information. So this is because the distribution is wider, right? So it's more flat. So that's why probably, right? So it could be other reasons, right? So it could be really centers around 2%. But in this case, you probably can collect more data before you make a decision. Is that what you are asking?
Yeah, probably. Just a little bit counterintuitive that those is described in probabilistic language. Because well, maybe you are modeling a distribution, but actually almost all the prompts are classified as bad or good.
Is it because like a probability statement is not convenient? Is that what you are saying? It's not like people prefer binary decision because it's simpler?
Well, I guess that maybe the models are just sometimes absolutely sure that it's not a jailbreak. Sometimes sure that it's a jailbreak, and then those probability calculations are almost always do not make sense.
Okay, all right. So you mean the data might not be reliable? Is that what you're saying?
Well, yeah, probably.
Yeah. Okay.
Thank you.
All right. Thanks.
Any other questions?
Yeah. Thanks for the perspective.
Probably no questions.
Okay, thank you very much.
Thank you. Thank you. All right.